talk about a little bit then about active vibration suspension, right? So we talked a lot about passive vibration suspension in this class, dampers and tuned masses. But active vibration can add energy to a system in order to mitigate the vibrations of the system, right? So we do this through a feedback loop. So we may have a system, like a mass here, and then we have a damper and a spring, right? So that's just kind of representing however our system is connected. And let's put an actuator here. This actuator, hydraulic actuator, it could be an air actuator. We watched videos of this before, right? But how this works is you're going to have a sensor signal, which is coming back to your control hardware. So that's your IEPE signal conditioner, maybe like a real-time processor or just a computer. And then you have some sort of control algorithm. So you have to have a way to select what you want to do. Then you're going to send a control signal to your actuator or your hydraulic pumps and provide some sort of feedback, right? So you're pretty smart. You can see a loop. I don't have to draw that because I can't. My pen doesn't work. So free body diagrams, right? So we can look at the equation of motion in the 1 degree of freedom, and we can give you a 1 degree of freedom system here, right? So we have mx double dot plus cx dot plus kx equals ft, and ft is our force. And we have a couple of forces. We have our force from our spring, our force from our damper, and then we have our force from an actuator, U. So let's call that FU. Does that make sense? Right? So FK, FC, FU. So a common method for providing control of vibration, right, is called position derivative control, or PD control. So we're going to drop the I out of the PID control. Have you guys talked about PIDs, the aerospace people? No? Okay, so we'll figure that out. So that's good. So proportional iterative derivative is a PID, but we can also do position derivative control, right? So this is the same math, it's just formulated in a different way. So a simple way to code a PD controller is to provide a control force proportional to the displacement velocity of the mass. So you have a force which is proportional with two gains, G1 times your displacement minus G2 times your acceleration. Right? So you have two little knobs that you want to churn here, where G1 and G2 are your proportional gains of the system. The control gains can be constant, determined by the designer. If you want to design something prematurely or beforehand, or variables updated through time with an algorithm. Here we will consider the gains to be constant. Therefore, the equation of motion for the closed loop system in Figure 5, right, becomes line 23. So we have mx double dot plus c plus g2 x plus k plus g1x. So now we can see that we can add synthetic damping by adjusting G2, and we can add synthetic stiffness by adjusting G1. So our controller, our actuator, it's best not to think of it as a way that adds force, but rather as a way that adds synthetic damping or synthetic stiffness. But because it's a controller in a loop, it can adjust that through time. This formulation lets G1 act as additional damping and G2 acts as additional damping. That is wrong. So G1 is additional stiffness and G2 is additional damping. Given this closed loop equation of motion, right, we can get a new natural frequency and a new effective damping ratio. And this is just for a constant system, but it's not through time, right? This is just natural frequency and damping.